This is tutorial 4, Laplace transform question 4. In this question, we are given the following RLC circuit, and we are asked to derive the differential equation and hence solve for the differential equation to find YT, which is the voltage across the capacitor, given some initial conditions. The initial conditions are at time 0, the current is 2A, as well as Y0 is equals to 1.5 volts. In this example, there's no external input circuit, so this is a short circuit, and XT is 0. The resistor given to us is 5 ohm, inductor is 1 Henry, and capacitor is 1/6. So basically, there's no outside signal driving the circuit, but there are initial conditions, and we're asked to solve for the differential equation. I now redraw the circuit, and we have the source, the resistor, the inductor, the capacitor, and the current running across, with resistor 5 ohms, inductor 1 Henry, capacitor 1/6 farad. Let's begin. We'll use the Kirchhoff's voltage law and say that the signal across the entire loop XT is equals to the current IT multiplied by R plus VLT, which is the voltage drop across the inductor, plus YT, the voltage drop across the capacitor. We know that the voltage drop across the inductor is the value of the inductance L multiplied by the differentiation of the current di dt. So that means the faster the current is changing, the more voltage will be dropped across the inductor. So it's L di dt. Although this is the correct equation, it does not relate YT to something we want. What is distracting us is IT over here. So if we can get rid of IT by casting IT to YT, that will solve a lot of problem. Let's see how. First, let's recap. The voltage across the capacitor VC of T is equals to 1/C integrate minus infinity to T I of tau d tau. So this equation tells us what is the voltage drop across the capacitor, which is YT over here, with respect to the current. We have another equation. The current across the capacitor is C dVCT dt. So the current across the capacitor have this equation. It is the differentiation of the voltage across time will give us the current flowing across this capacitor. Now we have a chance now to use this equation to substitute into here. And what about this guy? We can perform differentiation of this IT. So basically it's C d2VCT dt squared. But VC is across this capacitor, which is dy. So basically it is C. So this is the equation that we want. So now we have a way to capture these two equations. Let us now substitute. What we did was simply that we substitute what is IT over here, and now we use dyT over dt, and we also substitute this as dit dt. So this is the equation of xt. So now we have almost represented in the equation in the final form, we have y t as well as its differentiation, first order and second order with respect to the input. So this is the differential equation, but maybe we don't like to have these coefficients LC in front, so we divide both sides by LC, and therefore we have x of t divided by LC equals to C over LC is 1 over L, which is R over L dyt dt, plus then we have d2yt dt squared plus yt over LC. So this is the differential equations that is required for this question. We will now solve the differential equation with these initial conditions and the circuit values over here. Let's perform the Laplace transform. So we get 1 over LC, so this is Laplace transform x of s equals to, let's operate on this second order first. So we have s squared ys minus s y0 minus y, the first derivative, times 0. That's the initial. This is the two initial conditions that is required. Second one is plus RL, open up the bracket, s ys minus y0, and then plus 1 over LC ys. So this is the equation in the S domain of the differential equation. Now we want to bring ys to one side. So we have s squared plus r over ls plus 1 over lc is equals to, so let's bring the right hand side, which is xs over lc plus s of y0 plus y dot of 0 plus r over l y0. Substitute the necessary value, you can find that the answer is ys equals to 1.5s plus 19.5 divided by s squared plus 5s plus 6. What we now need to do is to perform the inverse Laplace transform to get y of t. I'll leave you to do the partial fraction expansion yourself. From this step to this step, you can try it manually or you can use residual in MATLAB to solve the problem. Once you have it in this simple form, you can simply do the lookup table. So we have minus 15 e minus 3t plus 16.5 e minus 2t. So this is the equation in time domain representing the voltage across the capacitor. This is my detailed working for you, showing you how to do use the MATLAB to perform the partial fraction expansion using residual and RPK expansion. This is the answer, and now let's plot yt. This is yt. Let's substitute t equals to 0. When t equals to 0, it is 16.5 minus 15, so it is 1.5. And the rest, we have to use MATLAB to plot. The other interesting thing to note is that as t goes to infinity, this becomes 0, this becomes 0, so it's 16.5 times 0 minus 15 times 0, therefore the final answer is 0. So y infinity is equals to 0, and this is y0 equals to 1.5. So typically in many of the questions, we'll ask you to find the initial and the final value. This is the code in MATLAB to this figure. Thank you.